Alright, first chapter for AICE Chem 1. Basically, it is a review of pre-AICE Chem. With chapter 1 dealing with moles and equations, and we'll get through molar mass, stoichiometry, titrations, balancing equations, nomenclature, all the basic stuff you learned in pre-AICE. So, always the most important thing, talk about chemistry, or actually anything in sciences, or math, or whatever in schooling, is why is it so important? And you can see from this diagram there's so much in the real world that chemistry is related to. Everything from medicine to obviously education, pharmaceuticals, the environment, forensics, nanotechnology, biochem, has chem in the name, so has to be important. Even law is important to know about chemistry because of patents, and then if you're suing the EPA or a pharmaceutical company about pollution, you should know about the chemistry as well. Alright, here is an example of a lab. So it's important to understand procedures. This one is basically a separation of process with distillation as well. Other things that relate to chemistry, you have Earth and space with geology, the nitrogen, oxygen, and methane cycles. Here you have the carbon cycle with acid rain and pollutants that affect our environment. The growth of green energy is important. Textiles, obviously plastic is very important. You want to make sure the plastic is more biodegradable but safe, using polymers. And pharmaceuticals is very important, obviously, to help keep us healthy and safe. So 1.2, masses, atoms, and molecules, the basic of chemistry, atoms and molecules. So how molar mass or atomic mass is developed was from carbon-12. Carbon-12 is the baby of the periodic table. It is the base of whatever atomic mass other elements have. Carbon-12 is exactly 12 AMUs, atomic mass units. And there's different mass terminology. You have relative atomic mass, you have relative isotopic mass, relative molecular mass, that's with a molecule, and you have formula mass, which deals with ionic compounds. So, do the terms really matter? Not really, because you're dealing with the same thing of mass. It just depends on what substance you have. Is it an atom? Is it an isotope? Is it a molecule? Is it a formula? But what do you really need to use to determine the mass? That's right, your handy-dandy periodic table. So, you should know pretty much most of the elements that you worked with in pre-AICE. We'll go through it pretty quickly. Just remember your left side and your transition metals are all basically left of the staircase. So you have your alkali metal, alkali earth, transition metals, the boron group, and then you get your metalloids, which starts with boron, and you see in the yellow. And then you get your non-metals starting with carbon all the way to the noble gases, halogens and noble gases to the right. The lanthanide and actinide series, those are your typical radioactive elements, even though there's mostly radioactive elements in the whole periodic table, but these are your traditional ones like uranium, plutonium, neptunium, thorium, stuff like that. So like I said, the weighted average mass is based on carbon-12, because carbon-12 has exactly 12 units. Here you have lithium 6.941, titanium is also a decimal, and cobalt's example 58.93. Why are they decimals? That's because of isotopes. You're not going to have exactly the same neutrons in lithium or titanium or cobalt or any other elements. You have averages. So an isotope, like I said, has different number of neutrons, but the same number of protons. You can't change the proton because that means you're changing the atom. So hydrogen always has one proton, but hydrogen 1, 2, and 3, which is called hydrogen, deuterium, and tritium, has different number of neutrons, but they add up to the total mass. So in hydrogen 1, there's no neutron, so it has a mass of 1. In tritium, hydrogen 3 has one proton because it's hydrogen, and then 2 neutrons to give you the 3 number. Helium has helium 3 and 4. Helium 4 is typically called alpha particle. We'll get to that. And you can see here lithium has 3 protons, but they have different number of neutrons, 6 and 7. 3 and 4 to give you 6 and 7. How do you write atomic mass? Isotopic mass? Mass number, which is the number of protons and neutrons on the top left. The atomic number, which is the number of protons on the bottom left. And then the element. You don't need the number of neutrons per se written on the symbol because you can figure that out by subtracting the protons and the mass number. That's also called the nucleon number, is the protons and neutrons. Relative mass of one molecule, so this is molecular mass using the periodic table. So carbon and hydrogen 4, which is methane, and H2O, dihydrogen monoxide, or water, can be found using the periodic table. The formula mass deals with ionic compounds. You have magnesium, which is the metal. You have hydroxide, which is an anion, a negative charged particle. And here you got sodium chloride, which is salt, table salt. Sodium is a metal, which is a plus charge, which is called a cation. And chlorine, which is a negative charge atom, is an anion, non-metal. So you can see molecules are your 2 nonmetals. Here you got water, ethane, nitrogen gas. Here you got atomic formula units, ionic compounds, metals and nonmetals, or metals and a negative charge particle. Find the formula mass. Water, you should find 18.02. For ethane, 30.07, and nitrogen, 28.01. Units for molar mass, grams per mole. Should remember that. And then for sodium chloride, it's 58.44. Sodium hydroxide is 40 flat, or 40.00. And for magnesium sulfate, MgSO4, it's 120.37. So you should be able to use your periodic table to get these answers for practice, using your calculator or mental math.